This way, that is, even if you have another component, then it would be 3 cross 2 transfer function matrices, but always you will find that is this I plus G2 G1. Or suppose if there is now, suppose there is a noise eta, and here you have a sensor transfer function G3. Then what would be that? I plus G1 G2 G3 or G3 G2 G1. Okay.
We were talking about something related to the pole in that line. I plus B1 including something.
Coming to that.
Then that would be three cross 2.
Exactly. That is, if it is so, then simply it will be then U1, U2, U3, and in that case it will be W1, W2, W3. And now at this moment it is a 2 cross 2 transfer function mapping, then it will be a 3 cross 3 transfer function mapping. And what I said, that is, this is internally stable if this transfer function matrix belongs to Rh infinity 2 cross 2. Now what does it mean? You have to check whether these individual transfer functions, whether they belong to Rh infinity or not. That means each of them has to be, anyway they will be real rational, but the two main things you will have to check whether they are proper and asymptotically stable. Okay. So for the same example which we consider, that 1 by s square minus 1 and then s minus 1 by s plus 2, you will find one of them will become unstable. So then, that is, it belongs to Rh infinity 2 cross 2, that is, for that you have to check, or rather this is, you have to check whether each of the transfer function element belongs to Rh infinity. Yes. Kanika, please say. Now, at this moment, whatever we learn, that is in the, with respect to the transfer function domain. Same thing we can learn in the state space also. That too we will learn. That is, if somebody asks you, that is okay, that is, this is everything in the frequency domain. But the same thing we must be able to solve in terms of state-based matrices, right? That too we need. So, but like today, I'm not going to go towards the state-based. Tomorrow we will do that. But now I'll have to define the well-posedness. So before that, I was talking about, at the beginning I said that we will learn this definition of internal stability. What is the definition of internal stability? This is the checking condition, or it's a lemma. Why checking condition? That means if somebody asks you, that is okay, how to check whether this interconnection is internally stable or not, then you say this one or you write this one, fine. But if somebody asks you, that is what is the definition of internal stability, then what would you say? Similar to asymptotic stability. If somebody asks you what is asymptotic stability, what generally we say? That is whether, that is for a dynamic system, like if you have x dot equals to ax, comma x0 not equals to 0, then asymptotic stability means whether x0 goes to 0, that means whether x0 goes to the origin as t tends to infinity, right? Here also the same thing, but here we don't have only one, we have two systems, right? So if I say that is here x10 or x20, that is now my initial condition. Suppose as a whole I am mentioning x bar 0, that is initial condition of the whole interconnection, whether whether xt and starting from, that is xt is the state trajectory of the entire system, whether there is xt goes to 0 from x0 bar at t tends to infinity.
It's mainly
That is called the internal
probably
stability.
unstable pole zero cancellation. Now, please be careful. Unstable means
Including the j omega axis. Okay? So not only the pole zero cancellation on the right hand side, on the j omega axis as well. So this example we already took last day, so where you could see that is if we consider only this channel, if you had a single system, then what is your solution? R, right? That is, if we consider only this channel, R2X, then absolutely there is no
Right.
problem. Because then we say mathematically at least t pole zero will get cancelled out, and that is what we will be left with 1 by s plus 1 whole square. So this is no doubt it's a Bibo-stable system. But the problem is that is when you think about another
here
channel,
also the same.
if
Now
it is close to
become
x0 bar, a bigger x,
consider
that here is a disturbance.
because now you have this your interconnection.
That was a difficulty, right?
Systems,
In
not
between.
one.
That is when you
So x1, 0 is the initial condition for G1, x2, 0 is the initial condition for G2. Then as a whole, and you also excite the system, you subjected to non-zero initial condition, whether the whole interconnection goes to the original point. That is called, that is as if this is the asymptotic stability of the whole interconnection. That is called internal stability.
Okay.
Once again, that is, if you extend the concept of asymptotic stability
That we
to an interconnection, not to only one single system, but rather an interconnection,
That
then
is
that
about
is
that.
nothing but internal stability.
So you have
So
understood.
that's why,
that
as in case of one system, we say that is whether this xt starting from x0, whether it goes to that is
few
zero
of the
or
channels
not,
will give you
at
stability,
t to infinity. Here also the same thing. We will say one or more, and like another x0 bar, another channel can give you an unstable transfer from 0, 0. And in that case,
As t tends to infinity,
then provided all
discussed
exogenous signals are
y
zero.
is the total response.
But the unforced
Then it will be that is y due to r non-zero, and d in equals to 0 plus y r equals to 0 and d in non-zero. In that case, what will happen? This one will be bounded, but this one will become unbounded.
Here,
and then their summation as
so far we have discussed
that is
everything.
it will the
It
y
will
will
zero.
go unbounded.
But in the
That is
definition,
the problem,
why
because
I'm taking the
in
help of
particular
the initial
situation,
condition,
we
right?
cannot guarantee
Internal stability
that
means
the always
you are
zero
trying
will be
to
perfectly
explore
safe.
the internal dynamics of the system.
Practical situation.
When we talk about the transfer function representation, it is only an input-output representation,
So,
right?
our main
And that is
task
also
is
the
to
reason
say
that we have seen that is if there is a pole zero cancellation, then R2Y channel will always remain Bibo-stable.
controller design. There is
So only if we think about only Bibo-stability, then actually a major part, or maybe if there is unstable control cancellation, internally there is a big massacre, but we are not taking care of
that is
that.
going to cancel with that.
So that's why there is internal stability concept. So in the asymptotic stability, that is a mode that gives more insight than Bibo stability. That I hope all of you will agree with that word. That is internal asymptotic stability. It gives more insight than Bibo stability. Why? Because Bibo stability is defined only with respect to input-output connection. But asymptotic stability, each component checks the behavior of the internal states as well. But that's why now state is coming into the picture. Internal stability is also about that is what is happening internally as well interconnection. That's why we are like borrowing the definition of internal stability and we are applying to this whole interconnection. That is the reason why I am taking the help of initial condition. That means gradually I am migrating to time domain expression from the transfer function. I am coming to the definition. That is how to check. So for this entire thing, that is in the next day we will see if I consider x and state of their the exogenous G1 and U, they are the internal signal. Then of course there will be a mapping input to output, and this is going to be a 2 cross 2 transfer function, and that to be discussed. X1 is the state for G1, so x2 is the state for G2 of S. Then and then it will have a whole A matrix. Suppose that is a capital A matrix. So then you have x1 into x2 function matrix, right? And then plus first of all R of S1, and then inside T1 S.
internal stability means this transfer function matrix. Now here we will have each of them is a, from now onwards we will have this representation. 1 to this 2 1 entry, this is 2 2 entry. Right? Internal stability.
So
means
then
this
this is what
transfer
happens.
function, this
That
transfer
is,
function matrix.
and all the extraneous signal, that is they are zero. Okay. Now,
So
if we are going to learn a new
equals
equation,
to
right?
zero,
That is, then what happens to the remaining part? If all the extraneous signals are zero,
Then it becomes AX1, X2.
and then you see, then U1, U2, they can also be inducted within the state, isn't it? Because Q1 is your W1 plus Y2. Now W1, if it is 0, then U1 equals to minus Y2. And then finally, in the time domain, this Y2 would be C2X plus D2 Y2. Right? So that means this one, Y1. So in that way, everything can be clubbed within this state A. So finally, what we see, well, this is the state space representation of this entire interconnection. And then there is, if all the extraneous signals are 0, you can ask me under that, what is this concept of whether this x1, x2 goes to origin starting the space x0 and then matrix that is called entire function space. Similarly, this is the space of transfer functions. So that is the transfer function space. Now, what is the power one is R8 infinity. We have to like decode to minimum. That's what
So
I
if you
tried.
see the matrix, 0, 0.
First of all, this H one here. The space of all holomorphic functions. Okay, so H is come. Actually, this U and this U, they are not.
This is time like
No, not only that. That is what we were also studying. So what will happen? That is in the state base. Like finally, this is the solution. Here, if you see, that is this is the U1 and U2. They are the combination of W1, W2 with this. But this is nothing to do with the initial condition. Exactly. But in the state-based domain, even if the extraneous signals are 0, but subjected to non-zero initial condition, there will be something, right? In the transfer function domain, we have one kind of approach, or rather we have one kind of expression, and in the state-based we have another kind of expression. Ultimately, they will become the same domain object. Okay. Okay, so here that is we will derive, that is what is that's what I said. Yes. Like tomorrow that is I will show you that what is the ABC, what will be the ABCD matrices of this whole interconnection. Then it will be completely clear. Immediately the question will come, what is holomorphic? You might have at this moment here that is I have written in the form of just differentiable. If it is open loop, then W1, W2 as of one you to both would be there. But the moment you close the loop, what will happen? This complex analysis you will be inducted here. Holomorphic and analytic, they are equivalent. The meaning are not exactly same. Then what I finally wanted to mean, that is this state. If it is x1, x2, whether that state vector goes to 0 starting from the initial condition under the unforced condition. Okay, that is called the internal stability. That means they can be differentiated. And now that is about that's one last thing. Is the well-posedness. Well-posedness last day. What did I explain? That is whether the signal exists, right? In time domain, that is whether you get a unique solution to the differential equation of the closed loop system. I explained with respect to differential equation. Now in the frequency domain, what will happen? You see my U1, that is this entire thing into what does it this entire thing into W1, the set of transfer functions or W1. So W1, W2, they are like real-time signals. It will write H infinity and these factors. Say for example here I plus G1 D2 whole inverse D2, here I see I plus that is G1 D2 whole inverse. That is the gains which would be provided by these two transfer function elements. Now we have to check whether they exist or not. Right? Now that is, can you comment about that? They exist means at all the frequency points, it must be a finite. It should not go to infinity. How can we, but as a whole, what should I write?
So,
regulate
Array
that, or how
infinity
can we
means
maintain
it
that?
is a space of all real, rational, proper and asymptotically stable transfer function matrices. Once again, that is Array infinity. It is a space, or it is a transfer function space. Is right.
bounded.
It is
There should be
a space
finite,
of. It is
principle.
a space of.
You are
all
right, but
real. The
comma
problem is not
rational.
rational. Actually,
Comma,
that is, if you
proper,
assume that is both
comma,
G1
and
and G2
asymptotically
they belong to
stable
Array infinity,
transfer function
then actually
matrices.
you cannot deal with unstable systems.
So,
it is a space
Right.
of all
So
real,
that's why we
rational,
cannot simply
proper
assume that
and
G1 and
asymptotically
G2
stable
both of
transfer
them
function
will
belong to
belong
Array
to
infinity.
Now, of course,
Array
it
is not only for CISO, it has to be defined for NEMO. So that's why I have to put
That
that
is not
why?
now
Because
I
suppose
said
G1 is zero slant or G2 is zero
So,
slant. In the
now
definition
most
also
of the
you can
cases
say where we
like
need controllers
space
can't
of
be
all
unstable,
instances,
right? Transfer function matrices of dimension.
So, if you
cross
have a
them.
product
of one stable transfer function,
So
one
it can
unstable
be
transfer
square,
function,
it can be
then
flat,
the
it
product
can be
will
tall.
have the same unstable eigenvalue, right? So it doesn't belong to Array infinity. That is the problem. Here actually this R generally it stands for real. Okay. This is a mathematical research. And we just think about like why we have omitted the rational part. Finally, we the equations 5 and 6 transfer function space U1 and U2 starting. Last day I said well posedness, and last day actually discussed that if you call a function having transfer function, then already you have assumed that it can be represented by P of S by Q of S. That is the reason why I have theoretically find the solution. Let the difference, or rather RH means real hard space. When you are choosing the function exist or that object, all the coefficients would be real. And now when we are talking about transfer function space, already you are classifying the object in transfer function. That means it can be represented. First of all, they should exist and it should be corresponding to each and individual already you are initial points. So now in the frequency domain, so R, this is the expression, this is U1 of S, for this U2 of S is that, and now where it is complete function, and that we are specialized now, it is a kind of, because they are expressions which are not real time signal and real value as a ratio and suppose they are bounded as well. That kind of space. And on top of W1 and W2. Now, what kind of gain is being contributed by these elements? Okay, that is the matter of concern, right? Now we know that all these G1 and G2 they are real rational proper transfer functions. That will happen. That much we can guarantee. But if you say that both of them are asymptotically stable, then that is a highly conservative assumption. Right? Because in that case, what will happen? We cannot deal with unstable systems, right? So in most of the cases what will happen, one of them will be your plant, another one of them will be your controller. So we do not have like any choice over the plant because the plant can contain non-minimum phase zeros, unstable poles, right? And then during the controller design we have to take care of those facts. So in the controller design, that is, it is our responsibility. That means it should be the responsibility of the control engineer to design the G2, I mean the controller, so that I plus G1, G2 whole inverse, that remains stable or that remains asymptotically stable, right? Now, if it is so, that is why I am saying that, that is, if you can at least guarantee that is I plus G1, G2 whole inverse, that is asymptotically stable, that means at least starting from zero frequency and then to very high frequency, it will always contribute finite gain. The way I explained the H infinity norm by the Bode plot, if it is a CISO case, then your I plus G1, G2 whole inverse, simply 1 by 1 plus G1, G2, it would be another transfer function. If it belongs to our H infinity, its H infinity norm would be finite. That means for all frequencies, it will give you the finite values, right? I will. So if it is so, then we are done. I am explaining everything. Only thing that is you have to check that what is the situation at infinite point.
Infinite means you see that here we are taking the inverse, right? I plus G1 whole inverse. If you have a under if it happens that suppose both G1 G2 are by property, that means G1 still it is finite, G2 infinity, that is it will be non-zero. And in some cases, if it is equals to minus 1, then what will happen? This is the maximum gain. Okay, but if it is C, so then it would be the suppose in the 1 and K by S. Then it is 1 plus. If it is 1 by S, 1 as you keep on reducing the frequency, the magnitude will keep on increasing, right? Example for that, 18 infinity norm 1 is not S by U R plus S. Are you getting? And for similarly, for under, if you move to undamped from under, that is the plan we consider and feedback. We consider the unit negative feedback, right? So that is in terms of 1 by S, I write this is G1 and then G2 as S1. So it infinity norm undefined. Similarly, if you have 1 and now plus 1, so here also G1 infinity by 1, it will be minus 1 plus 1. Minus 1 at omega minus to 0. Because if S equals to 0, that will give you DC gain. But if it is infinite, isn't it? It will be minus 1. Is it right? Omega equals to 1. Yes. What is the doubt? Omega equals to 1. This will be that is fine. So this does S limit S tends to infinity undefined. You minus 1. Another 1. So 1 by S minus 1. At S equals to 1, it will be the real number. So it will be 1. Similarly for 1. So G1 infinity into G2 infinity, so that would be minus 1. Then, like, what is the crux? Any transfer function with the pole on the j omega axis or on the open right half. That is an example of an unbounded H infinity. So or in that case, H infinity norm is not defined. I mean, when it is going to infinity moves or not, the norm is not defined. Because when call that is this object has a H infinity norm or any kind of norm, that means the norm must exist. What is the meaning of norm? That is a very short exist. That means it must be a real number. Why that is coming? If you can easily that is argued. That is sir. Why you are considering at infinity at a particular frequency there is at one point or finite frequency. If it happens that the situation going to infinity or is unbounded, you are designing the controller. That is our job. That is I plus G1 so inverse ultimately that is what is the takeaway point. Any because otherwise ultimately that is this G axis or almost open right and fill doesn't have a finite plus G1 G2 whole inverse. So if the inverse exists at infinite frequency, then we are done. Define it because otherwise.
So here we have found out G1 infinity and G2 infinity separately, and then we have substituted there. So, but if we first find out 1 by 1 plus G1 G2, and then we whatever comes the expression, there we substitute infinity.
The same thing will come. Because when the expression here individually I am finding out and then I am putting, that is here, that is ultimately, that is you suppose this is this denote this one by t, then what will happen at t of infinity? T of infinity means all the frequency domain quantities that you have to put the limit provided they exist. Now in that case, it is not going to exist. Right? Symbol, that's why I wrote symbol as a non-symbol. Infinity means now when it is infinity norm, this is system infinity norm. Because for a vector also we can talk about one norm, two norm, infinity norm. For a matrix also we can think about one norm, two norm, maybe infinity norm. So this is system norm. So why it is infinity? In this case it is called H infinity norm. So H infinity norm of a system transfer function is defined as supremum of the gain values is more than 2 omega then the gain values over all these frequencies. The situation will go smooth, no problem. But at the finite frequency of a system transfer function. You can ask that is sir, why didn't you write the general one? I mean, which will accommodate both C2 and MIMO because in this when I will to take the transport singular time domain, maybe at this moment singular value is not known to all of you. That is the transient and very low sigma max of the steady state. So then at the infinity point it doesn't exist, meaning there will be a break during the transient condition. So that's why infinity point is equally important.
if a signal has to exist in time domain, and if you decide to carry out the analysis in the frequency domain, then you have to check for the entire frequency range.
All
Not only in finite frequency, you have to check the infinite frequency as well. Infinity. Sigma bar means sigma max. We will talk about it more later, sigma. But at this moment, just I gave you the concept of the well closeness and especially the condition and the situation. That is, if it doesn't exist at infinity, then what the situation? That means maximum of all the maximum omega. That is, when in the singular value you have, that is like sigma 1, sigma this, there will be one sigma max and one sigma b. So the maximum over and all sigma unit step. That is, this will always be our 1, right? And then suppose here at the W there is no disturbance. So this part is fine. So there is completely 0. So now Q1 will be this one. Now you see that is there is unit step, shouldn't be any problem. But all of a sudden, when it goes to very high frequency or theoretically at infinity, it explodes. But that is not a real phenomenon, right? Asymptotically stable system, and then if everything goes fine, it should not explode. For that, we will have to develop this transfer function mapping. Can you think about the situation? That is in the real time, what is going to happen? That is, you see, that is one sigma-bounded signal. It is just a simply unit step signal. And output Q1, that means the input here. This signal basically, this is a now step. And then, if you here at omega equals to infinity, now it plus function infinity. That means that unit step signal that is going to be multiplied by this I gain. That is absurd, discussing all this, okay? So that is the RH infinity means, and in that example, what did you see last step? That is, we started with a biproper system, but again, within the closed loop transfer function has become improper. That is the well-posedness issue. So that is in the from one aspect we understood that is biproper system it has become improper in closed loop whose and in the reason I discussed, and now later we will see that is. Now you have H2 norm to be finite. That is not only asymptotically stable. We need all strictly further about it, and then so at this moment that points is clear. That is, I will come back to that later. As of now, you please take down the definition. This RH2. That means this is a space of all real, rational. This is a space of RH2 I am talking about. This is a space of all real, rational, strictly proper and asymptotically stable transfer function. Fine up to this much? Okay. Or it okay. So RH2 is the space of all real, rational, strictly proper, asymptotically stable transfer function matrices. So what is the difference between these two? This proper means it can include both strictly proper and biproper. So in case of RH infinity, that is, it takes both strictly proper and biproper. But RH2, it cannot take the biproper cases. That means if you have suppose 1 by s plus 1 by s plus 4, that is minimum phase asymptotically stable, is H infinity norm is also finite. Okay, it belongs to RH infinity, but if you calculate this H2 norm, you will find that it goes infinity. The H2 norm will be infinite. So this one doesn't belong to RH2. That is, at this moment, that is H2. We don't know how to calculate the H2 norm. So at this moment, it is not known to you. That's why there is you are facing some confusion. So that's why there is I asked you only to write. When we will learn H2 norm, then definitely it will be clear to you. Okay. So as of now, what is the difference between these two? More or less the definitions are the same, but the difference is with respect to the norm. In one case, H infinity norm remains finite. In the other case, H2 norm will remain finite. And accordingly, the name has been given RH infinity and RH2. Okay, so only thing that is one fact is not clear to you at this moment, that is why this transfer function doesn't belong to RH2. Okay, that you keep us down, we will discuss it later, because for that I'll have to define the H2 norm, and similarly there is a system 2 norm, that is for that we have to, there is this mathematical formulation that we have to learn, not exactly along the same line, that's why I am not discussing at this moment. H infinity norm is pretty straightforward. Why? Mostly because of the Bode plot. To all control students, Bode plot at the frequency response is quite known to us. So once that is so, anyone can talk about the H infinity norm, because at least in CISO cases, that H infinity norm means the maximum frequency domain gain. And rather, that is whenever we talk about a gain of a system, that is a frequency domain gain, right? Because in time domain, it is really difficult to talk about the gain. So that's why whenever we analyze the gain of a system, we first translate the system, or we first convert the time domain expression into transfer function, then we go for the frequency response, we check the frequency response, usually the Bode plot, the magnitude plot, right? So once again, that is the maximum value over the entire interval is the H infinity norm. And if you have understood the definition, then the reason is also clear to you why a transfer function having a pole on the j omega axis or on the open right hand side, why it has an infinite H infinity norm, right? Because at that particular frequency, the denominator becomes 0, as a whole the function goes to infinity, that means gain is infinity. Okay? If I ask you, let me say it is a common sense question, that is this transfer function, that is why it is a gain. What did you say?
So the input gets scaled by some DC value.
Not DC value, that is also varying, right? Because at different frequencies you will have different magnitude. Yes, because when we write that is y of s equals to g of s into u of s, and so that means that is the input is getting multiplied by another quantity and we are getting the output. Now in the time domain, it is like there are many functions in between, like e to the power something, then integration, so on so forth. So that's why we directly don't get the feeling of two gains, or rather the input being multiplied by a gain. Although ultimately they will be the same, because that is nothing but the Laplace inverse of y of s, but still in the time domain, mainly because of the convolution, we don't get the feeling of the gain, right? But in frequency domain, what happens, that is ys equals to g of s into u of s. U of s, that is a signal that is being multiplied by g of s. Now whenever you are talking about this multiplication, I mean the simple product, of course that is impossible in time domain, because in time domain two quantities, like two time domain quantities cannot be in product form, right? Of course they will be in terms of convolution. So that is the reason, that is when we talk about the input scaled by some other values, that concept is right only in the frequency domain, because the moment you convert it into the time domain, then it becomes what? GT convolution UT. You cannot write GT into UT, isn't it? In the frequency domain, when we write that y of s equals to g of s into u of s, that is simply point by point product. Okay, so here we call that is this input value is being scaled by the values this contributed by g of s. And when we see the frequency response, whatever the graph you get, that means those amount of gain is being provided by g of s. But the moment you convert it into the time domain, then y of t, what did you write? That is this impulse response g of t, not simply into u of t. That is absolutely wrong. It is a convolution. And if you have to remove the convolution, then you have to write that integration 0 to t e to the power all those things, right? So that is what I was talking about. That is, in the time domain, we don't exactly get the feeling of a gain, but which is pretty straightforward in frequency domain. Okay? That means output, that is where there is some gain is acting on the input signal, and the input signal being scaled by that gain. Okay, that is basically that is the concept of gain. Now, if the gain remains finite, then it belongs to RE infinity space. And the moment you have a pole on the imaginary axis on the right hand or on the right hand side, immediately at that frequency the gain becomes infinite. So that's why H infinity norm also becomes infinite, or we say it doesn't exist. Okay. Now at the same time, if somebody asks me, sir, what is the meaning of this RL infinity? RL infinity means that is the space of all those transfer functions whose A infinity norm would be finite. Now H infinity and L infinity, what is the difference between? That is, if you have some transfer functions that doesn't have any poles on the j omega axis but maybe right hand side pole, for them also, that is, we can define an H infinity norm not with respect to omega but with respect to S. We will see later. Okay, are you getting the difference? That means that is the exact reason why we sometimes prefer Laplace transform over Fourier transform. Are you getting my point? That is, if you have a transfer function 1 by s square plus 1, that means it is simply 1 by minus omega square plus 1, its Fourier transform doesn't exist. Why? Because on the boundary, that means on the j omega axis, it has a frequency. So there, that is, if you, the moment you put omega equals to 1, it doesn't exist. So for this kind of transfer functions, Fourier transform doesn't exist. But in control system, we work with unstable transfer functions, then how do you survive? That's why Laplace transform is more useful to control engineers than Fourier transform. Because, and then what is the fundamental, like what is the actual reason? In Fourier transform, the region of convergence is the whole j omega axis. And in case of Laplace transform, what do? You shift the j omega axis in the right hand side. That's why the sigma comes into the picture. From j omega, it becomes plus sigma plus j omega. Now the function which is like not integrable on j omega axis, that can be integrable on sigma plus j omega axis. That is the reason. Once again, the function which is not integrable on j omega axis, that will become integrable when you add that sigma. So that's why for unstable transfer functions whose Fourier transform do not exist but their Laplace transform exist, and in that way we can do our analysis. Okay. So in that way, that is, L infinity norm can also be defined. At this moment they are not required, so that's why I am not going to the, basically this is defined to cover the unstable transfer functions. RL infinity means only the left hand side part, RL infinity means right hand side part is also available, but the j omega axis will be separated. Okay, they will be excluded. So in that way, that is similar to H infinity and H2 norm, L infinity and L2 norms can also be defined, but they are not required at this moment, so that's why I am not going in that direction. But now that is this overall thing, that is, you please check once again and then I will come back to internal stability. We have to find these four elements, I mean these four transfer function elements. Okay. Now that is, you have understood the meaning of RH infinity. So given any interconnection, if somebody asks you, check whether it is internally stable or not, then what would you do? That is, simply you will have to find out this transfer function mapping, and then you will check whether this individually transfer function elements belongs to RH infinity or not.
That will be a tedious task to do.
No.
Because instead of 2 blocks, if someone gives us a 3 block system or 4 block system.
But there is immediately after this you will find whatever may be the number of components, I plus G1, G2 whole inverse, that will remain common to all of them. That we are now going to derive.
Sir, is it continuation of the last class problem? So
Then
then in the last class, G1 and G2 were interchanged. That one was G2 and this one was G1.
okay, that is not a problem. That is here, that is I have like written in that respect, because after this I am going to redraw this diagram to this. Okay.
So but this transfer function matrix has G1 on the 1, 2 element and G2 on the 2, 1 element.
No, that is the last day, that is we derived individually, right?
Yes.
That is this R2Y, and then in that way.
So whole matrix also you asked to find.
So whatever that is, you are saying that is if I take this is G1 and G2, only the mutually it will be different, okay? See, the poles or the zeros of I minus I plus G1 G2 whole inverse and I plus G2 G1 whole inverse, they will remain the same. So that's why even if you change the order, there will be the mutual shift. It is like there will be no problem at all. Here also that is I can do the same, but the only reason that is I chose this one to be 1 and 2 because after that I am going to shift in that way, and then the input out for input output I am going to write these notations. W1, this is suppose U1, Y1, this is my W2, this is U2 and Y2. That is the reason why I consider this is 1 and the other one is 2. Because as if suppose this is the input to the system, so U suffix 1, this is the output of the system, Y suffix 1, similarly this is U2, Y2, okay? And first exogenous signal W1 and second exogenous signal W2. So this one is just an equivalent word, not equivalent, simply this is redrawn. The first diagram is redrawn like this. So here, and these notations or the signal notations are new. Why? Because we have to now that is understand the common notations whatever used in the robust control books. So this Y, this W, this term or the signal W, that is this W is generally designated for exogenous signal. So what are the W candidates? It can be R when it is reference, it can be D when it is a disturbance, it can be eta when it is a noise. Now again D can also be DO, which will denote the output disturbance, or even D in if it is the input disturbance. Okay. In robust control, there we will be dealing with 4 kinds of signals. That is, one is W, then second one is the U. Generally U stands for the control input. Another one after that will come Z. Z means objective signal. After that Y and YM. Y means output, YM means measured output. Output and measured output. When we learn the generalized plant, then all these 4 notations will come into the picture. Have you understood? That is why I am using the W. And also there is the reason, because for this part you can refer the first part of chapter 5 from Kevin Chow's book. This one, I think I already uploaded this one. Robust and Optimal Control by Kevin Chow. This is a very good book, but the problem is like this is for the beginner it is tough. So that's why that is I always prefer the other one, Skogestad Postlewaite, as a textbook for robust control. That is the reason why I uploaded that one at the beginning. And I said that is you read chapter 2, 3, 4 as prerequisites, and then maybe 6, 7 and half of 8 as that will be the main content form itself. Okay. This is also a very standard book, but as I said, the problem is for the beginners it will be difficult to understand. But this internal stability and well-posedness, for that this book is really good. And maybe I also in my message last week in the post I mentioned that is you see the first 7-8 pages from chapter 5 of Kevin Chow's book for this internal stability and well-posedness. Okay, so that is the whatever that is I am teaching, that is in short you can find in that book. Okay, and specifically that book has used all the exogenous signal for W. That is the reason I am using W. Okay, and you can see that is usually we write this one as a P plant, or even that is simply G, means like we use both these like letters P and G to denote a plant, and then we use a C to denote a controller, like either C or K. This is for controller, and P or D, this is for plant. But from now onwards, we will understand, or we will look at it as if it is only an interconnection of two systems. Okay, we don't know which one is plant, which one is controller. So now the theory, whatever we are going to learn, so of course there will be multiple summing points, and the summing points can be interchanged. And when you have multiple summing points, then one can be treated as plant, another one can be treated as controller. Ultimately, when the stability property is of concern, then we have to check the transfer function mapping of the entire interconnection. So that's why from now onwards, that is, we are going to drop the convention of plant and controller. Rather, we will use the general notations G1, G2. The same thing in Kenninghau's book, they have used G and K, or sorry, P and K. That is, this one, the top one, they have written P, and the bottom one, they has written K. Okay. So that is what I am following. That is a G1, G2 or G2, G1. That simply you have two systems and now they are interconnection. Okay, and this is called a feedback interconnection. With respect to this diagram, I am now just going to derive all those four transfer function elements. Okay. Among these four signals, that is four letters we have just learned with different concept. I mean, one is W, then Y, U and Z. But I believe only the Z is completely new to you, right? W you have understood, exogenous signal. U, control input. Y or YM means output or measured output. But what stands for Z? Can you tell me? That is a Z, already I mentioned, that is an objective signal.
Reference.
Can anybody tell me that is what is the meaning of objective? No, reference will come under the W, because that I already said. There is W, under W, whatever exogenous signal, whether it is a reference, disturbance or noise, it will be regarded as W, exogenous signal. थोड़ा सोच के बताओ, ऑब्जेक्टिव सिग्नल का मतलब क्या हो सकता है? बस पहले ये सोचो कि हम लोग ऑब्जेक्टिव का मतलब क्या होता है? What do you mean by an objective?
Error signal that have to make 0.
Error signal, if it is a tracking problem, we'll have to anyway make error signal 0. Okay, but in I asked, that is objective signal. So you mean to say that is error can be an objective signal, output can also be an objective signal. But first we'll have to understand that what is the meaning of the term objective signal, right? I agree, that is both of them will be.
So ultimate goal of the signal.
So the pendulum of a clock should tick at 1 second. So that signal can be an objective signal.
So
Pendulum of a clock should tick at 1 second. So it can be an objective signal for the machine.
ultimately the theta or the output. So first of all, that is if I ask you, that means that is if I ask a control engineer, what is the objective? That is when when a control problem is given to you, then first of all that is we like look for the objectives, or it means what needs to be achieved. Now the moment you search for that is what needs to be achieved, then what other things will come to your mind?
Overshoot and settling time.
You were talking about performance. Before that, like what is the first criteria? Stability. So whenever we think about a control system design problem, what are the main objectives? The primary objectives is stability. Then you have performance. Right? Now, the performance, there can be different type of performance. One is the time domain performance. Another one is the frequency domain performance. And then you can talk about the error coefficients. So first major objective is stability, and then your performance. The performance can be very different. It can be time domain performance, it can be frequency domain performance, and it can be error coefficients as well. Now time domain performance means the one you said, that is rise time, peak time, then peak overshoot or even undershoot, all those things. I mean transient performance, that is my time domain performance. Frequency domain performance means gain margin, phase margin, bandwidth, critical frequency, all those, okay? And then error coefficient means when we talk about the KV, KA and KP. Frequency domain means it is the GM, PM and then bandwidth, PW. Resonant frequency as well. Time domain means we talk about the peak overshoot, like percentage overshoot POS, then the TR, TP, TS, etc. One other type of performance is also there, which is called that IAC, ITAC, IAE, right? Have you heard about that? I hope all of you have heard. Integral square error. IAC, very common. IAC, IAE probably, then ITAE, there are 4 or 5. Now, IAC is very common. IAC means it will be optimal. Design and use study such that this is one of the optimal performance criteria.
So it's a
Integral square error.
LQT problem.
Not LQT. This is IAC problem. LQT means linear quadratic tracking. LQR, there the performance, this is kind of a performance index. Like here you can write E transpose and then the Q would be simply an identity matrix into E. Then if it is E1, E2, E3, then simply it will be E1 square, E2 square, E3 square. Okay? Why you tend to think towards LQR? Because in LQR, what is the J?
XTQX plus
X transpose QX plus
UTI.
U transpose RU dt. Now, if somebody assumes that is Q equals to I and R is also equals to I, then this will become X square, right? And this will become U square. Now, here we are dealing with E square. Or you have replaced this X as if, like suppose if this is Y transpose QY, or here we can, there is another candidate would have been Y transpose QY. another candidate would have been E transpose QE. Now a tracking problem means E transpose QE. Similar thing. But here, that is there, the Q is not fixed to I. Here Q is fixed to I. This is simply the integral square error minimization.
So this is like version of that.
But it has like different performance application. Okay. So in such cases, so these are all different type of objectives which we are trying to attain, performance related, right? And then, so in that case, on which variable we are trying to achieve? On E, right? So then E is the objective variable. Now, if somebody says that is this, you have to go for disturbance attenuation, or like what is disturbance attenuation? That is, in this case, that is, you have to suppose this is Y, and YT means it will have the component due to R, it will have the component due to D0, or rather I can write D in because it is input side. So that is what I'll have to do, that is design the controller so that the gain of this channel is minimum. Are you understanding what I am saying? Because इसका जो इफेक्ट है उसको पूरा नॉलिफाई करना इम्पॉसिबल, क्योंकि ये जितना देर तक डिस्टर्बेंस इनपुट रहेगा इसका इफेक्ट भी रहेगा, हम लोग उसको पूरा नॉलिफाई कर नहीं सकते हैं, बट इसका जो इफेक्ट है इसको रिड्यूस करना या मिटिगेट करना हम लोगों का ऑब्जेक्टिव है, राइट? तो इसको हम लोग क्या करते हैं, ये जो D in to Y ये जो चैनल है इसका H infinity नॉर्म हम लोग मिनिमाइज करते हैं, so that इसका जब ये जो when the D in is acting, then of course there will be its effect, but that effect will be minimum. So here what is that disturbance attenuation means? You have to minimize the gain of the disturbance channel. D into Y, that means from D into Y you will have a transfer function. It will, the controller will also be there included in that component as well. So design the controller so that the tracking is, like tracking should remain unhampered, and at the same time the gain of this disturbance to output channel should be minimum. That is called disturbance attenuation. So here what is your objective signal? किसके ऊपर हम लोग काम कर रहा है? Y के ऊपर. So here the Y is your objective signal. So in different circumstances, this E, Y, U, all of them can be your Z. When it is an error minimization problem, then E is the Z. When it is a disturbance attenuation problem or a tracking problem, then Y is your objective signal. If somebody asks you, that is, you have to design a minimum energy controller, then your objective signal will be U, because U का norm minimize करना पड़ेगा. Have you understood? That is what is the meaning of objective. So in different types, so for achieving different type of performances, in one of these signal or even combination of them have to be treated as objective. So that's why they are called objective signals. Usually we may think that is okay, output is the objective. No, because you may have to achieve something on error signal as well, maybe on U signal as well. Once again, if it is an error minimization problem, then E is your objective. If it is a disturbance attenuation or tracking problem, then Y is your objective. If it is an energy minimization problem, then U is your objective signal. So each of them can be a Z. So Z is not a separate signal. Actually, some of them or one of them is classified as an objective depending upon what is your requirement. So these four signals or these four letters, basically W, Z, U and Y, they are quite well known in ROAS control. After that, when I will draw the generalized Planck block diagram, that is, so far you don't know, that's why maybe you are not able to relate. So there in the generalized Planck block diagram, every time you will see this kind of notation. Okay? So then that is coming back to here. I hope that is all this discussion are going fine and you are understanding. See, while teaching, that is, I try to mention many other related things so that your overall knowledge grows up. Okay, that is required. So last week when we took up this, for that I think all of you can like easily find out the relations. That is like R2Y, sorry, R2E, R2U, and then D into U and D into E, right? Here how could you do? That is last day when we were doing, then there is individually we suppressed one of the input and we found the remaining ones. But what is the generalized procedure? That is, if I ask you, that is without like making one of them 0, keeping both, can we find?
Keeping R and D in both in a band.
Huh. That means both the input terms would be present simultaneously. In that way, can we do the simplification and ultimately to find out the relation? That we should be able to do it, right? Let's see. Then, first of all, there is everything we are going to do on the frequency domain. So you should use the capital letter. Okay. U1 of S equals to Y2 of S plus W1 of S. This is one, and then my U2 of S equals to Y1 of S plus W2 of S. Okay.
So U1 of S minus Y2.
Oh, right. Actually, I wrote plus because in the Kennington's book, they inducted this minus with this. If you see Kennington's book, I am mentioning because after that, if you see that book, then you may get confused. That is this minus sign. If you drag here and then if you call minus G2 to be G2 hat, then what would happen? It's a positive feedback interconnection of G1 and G2 hat. In that book, they have considered accordingly. So this one they have used P, and this one they have used K, but another notation you will find K hat meaning is the minus of K. But anyway, that I am not doing. That is just for your information, so that when you will go back to that book, you should not have any doubt. So now the standard relation.
Plus, that will be plus. Minus should come before Y.
Oh, yes. Thank you. Then now standard relation is Y1 of S equals to G1 of S into U1 of S. That is my standard relation. And then Y2 of S equals to G2 of S into U2 of S. These two are also my standard. Now only thing that is we have to replace, that is what we want, that is like both the expression of U1 and U2. Okay, both what we want, that is U1 of S equals to something into W1 into W2. That means we have to replace both this Y2 and Y1. That means here we need something into W1 of S plus something into W2 of S. Can you do that? That is really easy. That is, you u1 equals to minus g2 u2. Just to save some time, I'm not writing in brackets, but you should write instead of w1, and then minus g2. What is my u2? The second one, y1 plus this, y1 plus w2. Then what is my y1? g1 u1. So this is g2 into g1 u1 of s, and then what will happen? Minus g2 w2 plus w1. Are you getting all of that? Please take this term at the left hand side, and then what would happen? That is I plus g2 g1 into u1 equals to minus g2 w2 plus w1. I hope fine for all of you. So u1, that is equals to, we are multiplying both sides by I plus g1 g2 inverse on the left hand side. Please be careful about that because it is matrix multiplication. So order is really important. So this time you are multiplying both sides by I plus g1 g2 whole inverse from the left hand side. That means you are 3 multiplying. Okay. So this is inverse. Of course here it will be, you have a minus g2 w2 plus I plus g2 g1 whole inverse into w1. Have you seen this I plus g2 g1 whole inverse is common? That is the thing I said. That whatever may be number of elements, the core will remain the same. That means pole will not be the different. The set of poles will remain for all of them as long as there is no pole zero cancellation.
So, but G2 will also contribute some poles, right?
If, like lastly you will see that is there will be only some of them that is may get cancelled out, and mostly zeros will be different. Yes, some of them that is would be like after all the adjustment you will see that it will be different. But I plus G2 G1 inverse, the core part will remain the same.
For all the combinations.
Only that is somewhere you will find here like G2. Here there is nothing. In one case you will find G1 will come, like after this we are going to find the U2, and then we are going to list. Then you will find even in U2 also, in both the terms I plus G2 G1 whole inverse will remain common. Now similarly, can you find the expression for U2?
Sir, in that summation, y1 is added or subtracted?
Subtracted.
In the middle one. Which one?
Here? ये तो प्लस है.
So y1 is added.
ये according to this one only. All of you please see that this is just like a new version of this one. That means keeping this as it is, I have that is like drag everything bottom. So that's why that is this will go down here and this summer will go down there. Okay, that is the case. Nothing. Only these two are that means the same thing. And then how to find U2? Then U2 equals equals to y1 plus w2. That is g1 u1 plus w2 equals to g1 into, again my u1 means minus y2 plus w1. So it's minus g1 and y2 means g2 u2. Isn't it? Just I'm going to write them formally. U1 of s, U2 of s. Now this is my U1 of s. So this will start from I plus G2 G1 whole inverse, because W1 is the first entry, so that will be here, and then minus of I plus